Okay, this is my talk about designing secure databases. So, my name is Dominic Tarr, and that's the name that my parents gave me. And I was generally pretty happy with Dominic, but then I became a somewhat notorious JavaScripter, and I had a problem. There was another Dominic, and he liked promises, I liked callbacks, and so on. So, but the problem gets worse. So this is a graph. Oh, hang on. This is a graph of the popularity of the name Dominic. So, see, I was born around here, I was accustomed to be pretty much the only Dominic. And now, it's beginning to look like, so I want to make this graph look like a graph of Bitcoin prices. So I'm going to change my name to Zuka Dansan Zamaz Hobev Hudot Rotiv Gabon, so on. So this is the ProQuint encoding. That's a pronounceable binary encoding of the hash of my public key. Now, this is a much, much better way to choose a name, because no one else can choose the same name as you, and yet you do not need a private, you don't need a registry or anything like that either. So no matter how many people there are who try to make up a name, they can't steal my name, and I can prove that I have it. You can also represent it as emoji, and emoji is also really good, because if you've probably already memorized the start of my name as emoji, because it's like in the corner there's tomato telephone, the earth faced on Asia, a gas pump and stuff like this. And so if each of those are one byte, you've already memorized the equivalent of 8 hex digits, which you never would have done if that was a hex number. So, yes. So, there's two things going on here. Hashes, which can be used to identify data securely, and public keys, which can be used to identify users. So anything you sign is proves that you authored that thing, and and when you want to refer to exactly that thing, you can refer to it by its hash, no matter where it is. So we're familiar with hash tables. It's hash tables and cryptographic hashes, and there's an important distinction between these things, because when you have a hash table, you expect to have some collisions, and part of the problem of designing a hash table is planning how you're going to have those collisions. But cryptographic hashes are very different. So with a cryptographic hash, you design a sufficiently strong hash that will never collide. So you just need to have a huge amount of possibilities, so that you'll never encounter one in practice. So to put things in perspective, so this is how many Twitter usernames there are. So it's like 3 with like 23 zeros. Now, there's more bacteria on Earth. So bacteria on Earth can't sign up to Twitter, not all of them. But they could have IPv6 addresses. In fact, there's enough IPv6 addresses for every bacteria to have 1,000 of them. And there's way more possible SHA-256 values. The only number I could find, real number I could find that's larger than that, is the number of particles in the observable universe. So we probably don't need to worry about it. So this is a graph of what various things that scientists will think will happen to the universe. All of these mean it is destroyed in one way or another. So we've got about another 15 billion years to go. And so if no collisions happen in that time, everything's cool. Or at least, I mean, we have much bigger problems than hash collisions. So we'll just, if we design a thing like that, we'll just like not worry about this problem. And so the other thing, asymmetric cryptography. Who understands how asymmetric cryptography works? Cool. So actually, all of you do. So there's this fairy tale. So this is the German name for it. But is anyone familiar with, know who this guy is? So Rumpelstiltskin. So this is a fairy tale about Bitcoin. So it's about cryptocurrency, and so basically this story occurs in many cultures. But so there's this drunk guy. He's the miller or something like this, and he has some great idea for a new cryptocurrency, and he boasts that like his daughter can spin straw into gold. And the king hears about this, and he's like, "Well, this is amazing. You must demonstrate this for me." But you know, when he wakes up in the morning, he's like, "Fuck! What did I say when I was drunk? There's no way I can do this. I don't know anything about cryptography." And then this hacker or this imp appears, and he's like, "I know how to do all of this stuff. I will implement your crypto system, and we will mint straw into gold." And he accepts his offer because there's no choice, because otherwise, you know, the king will chop off his head. But the hacker asked only one price. The price is the firstborn child of the daughter, which is a terrible price, but they have no choice but to accept. So he spins straw into gold. The king's very happy, marries the daughter, very impressed. Everything starts to live happily ever after for now until the first child is born, and then the imp comes back, and it's like, I've come to collect what's mine. And they're like, "No, we don't want to give you up." They don't want to give up their child, of course. So they're like, "Is there anything we can do to get out of this? Anything at all? Is there any other way we can that doesn't result in us giving you our child?" And it's like, "No, of course not. Not unless you can guess my true name, aka my private key." So the queen spends 3 days trying to brute force his private key, but it doesn't work. And just then, there's a messenger that's traveling through the forest, and he comes by some weird character in the forest who's dancing around his fire, and is like, "Aha, they'll never guess that my real name is Rumpelstiltskin." Reports this story to the queen, and she's like, "Aha." And when Rumpelstiltskin arrives after 3 days, they steal all of his Bitcoin. Now, it's very curious, I think, that this story occurs across many cultures. There's like, this is the name of the German version, which is well known in English because of Brothers Grimm. There's also a Scottish version, and a Hebrew version, and a Japanese version. It's like this pattern where there's a secret name that gives you, if they know your secret name, they have power over you, is basically how asymmetric cryptography works. And it's very curious that the ancients like somehow intuited this possibility, whereas we didn't actually figure out the math for how to create things like this until the 70s. So I think the only simple explanation for this is that aliens visited Earth in ancient times, and they happened to have advanced crypto systems and stuff like this, and they didn't, and the people at the time knew something important was happening. They got the gist of it, but not the details. So children already understand asymmetric cryptography. Okay, now databases. Let's apply these two things to databases. So when I started doing Node, I sort of moved through these phases, and learned more, and it's sort of taken me to the stuff I'm building now. So streams, do real-time changing data, replicating data simultaneously between databases, and just designing databases with indexes and stuff like this. I didn't know at the time, but I was actually learning how to build a secure decentralized database. And so there's a few things, I'm going to share with you a few things that I learned about databases. All of your favorite databases, they all suck. These all have like really terrible design problems, all of them. I mean, some of them are worse than others, but they're all bad. And they all have this one deadly problem in them, that they let users do stupid things with them. So what I've learned is that there's only two, so databases have this wings fall off feature called delete and update, which lets you overwrite perfectly good data that was already there. And so most databases lose data because they allow a human to tell them to forget something or overwrite something. This makes designing systems really hard. So there's actually only two good database designs. That's the log file and the content addressable store. And so we've always had log files. Content addressable stores are more of a new thing. So log file, you can append to the end of the file, but not in the middle. You can read from anywhere. So you can do searches as long as the file is in the order of the primary key, which is normally time. But if you create a new sorted log file, you can sort by something else. So records are ordered by the time stamp or sequence or something like this. And this makes replication of the log file really, really easy, because you read some of the log file, and then if you stop, if your connection gets broken, you're still in a valid state, and next time you just continue reading from where you were. As long as there's one writer to the log file, you can have as many readers as you like, and they just continue reading from wherever they were, and you can always start again, and it's really simple. They only need to send one piece of information to the master to find to catch up to where they are. Just the line number or whatever. So a content addressable store is another kind of database where it's not ordered, where the key to each piece of data, the key to each object is the hash of that object. So it's the key is determined entirely by the content. So it's impossible to update something. You just insert a new piece of data with a new name. You have insert, but you don't have update, you don't have delete. And this also makes replication this has some interesting properties, like, so hashes work just like links, because that hash effectively uniquely refers to the piece of data that has that hash. But also, you can't create links. It's impossible. Infeasible, I mean, because to know the hash of a piece of data, that data had to already exist. So if you create another document that refers to an earlier document, it, in a way, was caused by that earlier document. So it's impossible to go back around unless you can generate a hash collision, which you can't do before the universe is destroyed. So that's cool because we don't need to check that property, so we can get. It makes things easier. So replicating a content addressable store is also really easy. Basically, we just need to find out what hashes each side is missing, and then just send the missing data. And because we can never overwrite anything, we never need to work. We can write to multiple databases and just merge them together. We never need to worry about the problem that afflicts every other database that claims to have multi-master replication, which is conflict resolution. Now, this is like the sort of bogeyman that stops data replication from ever working, because there's basically, when you do see a database that claims to have multipass to replication like CouchDB, they always leave the conflict resolution up to the users. And the reason for that is because because database experts don't know how to do this, because there is no answer. It always seems like it's tantalizingly just around the corner. Maybe you just need to know a bit about how the application works. But when it actually gets into the hand of someone building an application, it's like, oh, how am I going to do conflict resolution? I didn't even think about this when I was starting. They just end up doing something really simple, like throwing away, they just did the most recent right of win, something like that, which is fine, I mean, but the people designing the database would have never, can't accept that they want to choose something this stupid. So better just not to have conflict resolution, just not to have conflicts at all, and then there's no need for conflict resolution. So there's sort of two patterns here. There's a log file and a content restore, which is kind of like a linked list, you know, a long structure, a long chain structure, and a hash table. And interestingly, Bitcoin is just a linked list. BitTorrent is a hash table. These are incidentally also the two currently really successful completely decentralized, completely secure database systems, if you will. Database in a loose sense. So yeah, Bitcoin is just a log file. But Bitcoin has some problems. So this is a graph of the amount of compute, more or less, the amount of compute that goes into calculating Bitcoin. And you see it's gone from not that much to fuckloads. This is like really expensive. So I was in Iceland recently, and I found out that actually 10% of the Bitcoin in the world is mined in Iceland. And Iceland's really good for this because you have a lot of cheap hydro and geothermal power, and you can passively cool your data centers. You just open the window, and you save a lot on air conditioning. Places where smelting aluminium is a viable business are also good for Bitcoin because it wastes a huge amount of power. Also, the performance, as purely as like as a database system, the performance is like incredibly bad. So Bitcoin is designed to do 1 megabyte every 10 minutes, which the laptops that you have can all probably do closer to 100 megabytes per second. So this is a really terrible way of creating a log file. The only good thing about it is that it's decentralized. But you only need all of this, something like Bitcoin, if you want to have this one thing that's strictly ordered, where one thing always comes after another. If you don't need that constraint, then you don't need a blockchain. We don't need one blockchain. So this is other Bitcoin projects that take sort of, they're like, let's hit everything with the blockchain hammer, and they take the entire internet and then put it into one blockchain. But obviously this is a really bad idea. However, I have a slightly better idea. Instead of one log, let's just have lots of logs. And instead of using an expensive proof of work thing, let's just use a very cheap signature. Let's just put one person in charge of each log. So everyone has a log file, and then perhaps you could replicate other people's log files. Well, that's basically Twitter. So most applications these days are basically Twitter plus something. There's LinkedIn is just Twitter for enterprise. Facebook is just Twitter for people you went to high school with, and so on. So this brings us to my project, Secure Scuttlebutt. So it's basically a decentralized Twitter That's the core data model. Now, so programming is pretty hard. And it's hard because you have to decide, you have to like get this dumb robot thing and you have to tell it exactly what you want it to do and be completely precise about it because it won't get like, you know, the gist of what you're trying to tell it. You have to be completely right about everything. But distributed programming is like much harder than this because now you're programming lots of computers, and because the speed of light is so slow, the computers can hear about things in different orders, and then so basically you have to do all of this, plus the things can happen in all crazy order, you have to make it work no matter what order they do. Now decentralized programming is even harder than that, because you get all of the earlier stuff, but some of the computers might be lying to you. So when you have computers that you own, it's relatively simple to make sure they're doing the right thing. But in a decentralized system, it runs on computers that you don't own, so they can kind of do anything. We have to ask, what does own really mean? And so this is an idea that sort of goes back in human history, but it basically means like you control this thing. And at the like, you know, in different kinds of things, you sort of requires different amounts of infrastructure to be able to own those things. So like, I can own my clothes pretty easily because things that I'm wearing, very easy for me to defend. Like you'd have to fight to get those things. But like my bicycle, for example, I have to add extra stuff to that. I have to chain it up so that no one can steal it, otherwise I'd have to be riding my bicycle constantly. For things like cars and real estate and this sort of stuff, these whole systems of, you know, you need police and lawyers and courts and laws and governments and then like the military to protect your property system from neighboring property systems. And this all exists to make distributed programming easier. But yeah, so you need to assume that decentralized computers can do whatever they like. Basically, so it gets worse as well. So if you meet if you meet someone who's like a total jerk, what you can do is you can just brand an X on their forehead, and then everyone will know to avoid that person. But it's not so simple with computer programs. So this is a graph of Gamergate tweets by account creation date. You know, this has been a sort of ongoing episode recently. So basically, a large amount of them were created in the last couple of months. And here is a script from 4chan advising how to create a fake account, make it kind of look real, and then start harassing people. Of particular interest, there's this bit on the bottom where it says, for extra class, present yourself as normal people who social justice warriors by their own standards would sympathize with, like an Indian cab driver who can't read traffic signs. So in the literature, this is known as the Sybil attack. Basically, an attacker generates many fake accounts and then attempts to compromise your network or mess with you and trick you into believing the wrong kind of thing. So, and in actual systems, this happens all the time, but manifests itself in different ways. So email is spam, and email is basically unsolicited messaging. If I have your email address, I can send you email. And because email was never designed to contend with spam, basically the only way to prevent spam is by mass surveillance. Like Gmail, Google just reads all of your email, reads everyone's email, and then analyzes it to be like, which is the dodgy email. And if you click on stuff and like, you know, it does all kinds of clever things we don't have to worry about that makes email usable. Twitter is actually simpler and avoids most of the spam, because Twitter probably clever enough to implement the sort of stuff that Gmail had. But the natural affordances of Twitter avoid most of the spam because Twitter is solicited spam. So when you follow someone, you're saying, I will read more or less anything you send me. You will read all of your spam, but you just don't follow the Nigerian spammers. They can still reply to you, but it's just not so much of a problem. So Twitter is naturally better for spam. So but Twitter also has problems because, there's still people who are abusing Twitter and stuff like this, and there's no simple solution to this for Twitter's perspective. It's not part of their business model or something like this. They don't make any money by telling jerks to shut up. And even if they were prepared to do this, would you really want them to? Because your idea of a jerk might differ from Twitter's idea of a jerk. It's just not so simple. So if you have a decentralized system, you need something else. And I think the answer is you basically need something like tribal law. So each group of community of people get to decide what their own rules are, and they have the power to vote someone off the island. So basically, you could just post a message that says, block this jerk, and then your friends would no longer give that person their data. Effectively, now they can't irritate you because they can't send any message to you, and they can't read any of your data, so eventually you've just completely blocked them off and ignored them. And so historically, certain cases, nearly all tribal groups and so on, ultimately, this is the thing everyone does eventually, is kick someone out. And in many cases in times in history, this is a punishment that's considered worse than death, especially if they put the brand on your forehead. So there's lots of ways we could approach this. You could point people to be the moderators, or you could just be I'm also going to shun people that annoy this one. There's one more important design consideration. So, who can spot the odd one out? Anyone? One of these people is different from the others. Okay. Any guesses? Okay. It's a trick question. They all turn evil. So this brings us to number one adversary for this crypto system, future Dominic. So we have to design a thing where me from that looks like about 40 years won't have turned evil. Now, this is a classic problem. So in America, they built railroads, and America's basically settled by railroads. And the railroad tycoons got these massive grants from all of the states they went through. It's if you build the railroad through our state, we'll give you 50 miles of land either side of the, where you build the train tracks. And then they would get this free land and be well, we'll go to Europe, we'll get a bunch of poor people and be hey, you can come to America and be farmers, it'll be great. And they're well, that's way better than being a peasant or whatever. So they'd move to America, move into this farm in the interior that was only accessible by rail, basically. And then once they've sold all of the farms, then they'd just jack up the price. And the farmers can do nothing except they just have to lump it because there's no other way to get their produce out. So they're basically totally screwed, except by the owners of the railroad. And you see this pattern on computer stuff as well. So you start off with a thing that's totally open and friendly and everyone wants to join it and be this is really good. And then once it becomes really successful, then you just turn down the thumb screws and people can't people can't use it how they want. They can only use it in the way that's profitable for the owner of the platform. And when you give someone control of the platform, the temptation to do this is irresistible. So what we need to do is design a protocol where you can't do this. Like HTTP really doesn't have this problem. You don't have to pay any money to Tim Berners-Lee to send an HTTP request. This is the way it should be. So, incidentally, for America, they don't have a train system anywhere near as good as Europe's, because Europe didn't give the railroad barons this crazy amount of control. And eventually, America did get an open transportation system of cars. Cars had their own problems, but you can go wherever you like with them and so on. So, some cool links. This is spread across a couple of repos now. There's Secure Scuttlebutt, and there's a user interface for it called Phoenix at the moment. And if you come and hang out in Scuttlebutt on ISE, we're talking about all kinds of crazy stuff. How are we doing for time?
We are over time.
Cool. Thank you very much.